All right, this is a more technical follow-up on the previous RH video. So this one's basically, it's still about the same sort of topics, just more involved, and I hope you guys like it. So recall the construction of the seed object. You take the four diagonals of the cube. And then we generate these surfaces with constant positive Gaussian curvature using the momentum profile of our 5 view, where A and B are determined by the optimization constraints of the cube boundary. And of course we're going to glue this these sheets together. Okay, so that yellow graph is gamma, but it's not completely accurate in this animation. It's more of a schematic representation. The real gamma actually is the outer pairwise intersections of that structure. So yeah, so each sheet of the seed, so each x sub I, has the same metric, action angle metric, given by that momentum profile I mentioned. So the goal is to build a positive quadratic form living on the seam graph gamma. And then we're going to want to match it up with a quadratic form of previous construction, which was the when you take the look at the cone local modes, and then you toggle from the cone local high energy modes with that theta function, Jacobi theta. You toggle to gamma via Fourier duality. So we're going to want, and then you can take the Mellon transform on gamma to get the completed Riemann zeta factor. But this, so here we're going to construct something else and then try to match it up with the theta sort of quadratic form, that method over there. So we basically put these Laplace-Beltrami operators on the sheets, and each carries and we eventually get a Dirichlet form. We have to define the Hilbert space. So we're going to define the Hilbert space of gamma to be L2 gamma, and then the measure d sigma is that measure induced on gamma by the action angle metrics. So we're basically getting that measure from the surfaces induced onto gamma. So we also have to specify matching conditions on the vertices. There's a lot that needs to be specified and done here. So now the next step is a harmonic extension from gamma. So we're going to solve this harmonic extension problem, and we're going to try to basically extend the away from gamma, such that the map P sub j extends the critical line data onto the jth sheet harmonically. So the effective operator on gamma we want dtn operators on the jth sheet. Then we're going to sum over the seed. Okay, so basically we want to turn the boundary we'll use Green's identity, but we want to turn this boundary stuff into the bulk energy on the sheets, and then we want to show that the gamma, basically positivity condition, is in concert with the seed, the entire seed, but we're really concerned about this gamma having the positivity condition, because that's the most important aspect of this whole thing. So the critical line theta states so we're taking the theta construction, right? So that was when we took the basically when we took we looked at the cone local modes initially, and we said, okay, we looked at the link, and the radial modes were stuff like Bessel's, and the angular modes were Fourier modes, and we summed the Fourier modes up to get a theta. In particular, we want a Jacobi theta, because it's easier. We get the Riemann zeta completed functional equation there, or completed function. So essentially, we're doing that, and we want to match up both stories to be equal, basically. So we just want some closure in that regard. All right, so the seed critical line quadratic form, Q gamma F. I'm gonna take this, and we want it to be greater than or equal to 0, because this is sort of like a Weil positivity condition or a principle. We want this to definitely be positive if we have any shot whatsoever. So if we expand that Q gamma sum expression, get a positive definite kernel below, and essentially now we're at the Mellon-side RH quadratic form. Okay, so we take this so W sub lambda is the distribution of the completed zeta function, lambda of S, and we want to identify that QRHF to be, or not identify, but we want to make it so that's positive definite 2. Okay, so we need a required comparison identity. So we basically want the kind of like the theorem, and we're looking for is the identity QRHF equals Q gamma F for every F in the immiscible class. So if it holds, then QRHF is positive definite, and RH follows from the established criterion. So that'd be cool. And this is this target theorem is conditional, by the way. It's not unconditional at all at the moment. So critical line Laplace-Beltrami representation. So we got S, the 4-sheet seed, identical action angle metrics, identical conditions along gamma, N sub gamma as the induced effective operator, and we're going to assume the comparison identity QRHF equals that, then QRHF is positive definite. positivity criterion. And there are a bit of things that need to be verified. Obviously, so number one, the common boundary value problem is well posed. That's a must. 2, n gamma is self-adjoint and positive on its domain. The vertex conditions on gamma are specified. Number 4, the psi t coincide with the theta data giving lambda of s. T sub gamma is defined on the full class, unmissable class, yada yada yada. There's a couple more. But importantly, no residual term remains in RF equals QRHF. So that difference has got to vanish. So yeah, basically the decisive calculation right there. I mean, previously I was thinking like you needed to identify like somehow the critical strip of the seed with a critical strip of the usual like complex plan that the Riemann hypothesis is usually presented in, and you don't. I do not think you need the primes either, because this all takes place like the seed is somehow an extension or an enriched way of thinking about the critical strip. So I don't think the primes are needed, because you could construct that as an alternative, like extra information, extra context to solidify or back up the proof. But anyway, thanks for watching. Hope you enjoyed, and like, subscribe, comment, ask me questions. Thanks. Bye.